have to look at three basic, simple concepts: a random pension global system. And you have to compare it between the SolidWorks motion analysis and the analytical analysis that he did by hand. This is the pendulum system. Mind you, when we started this whole thing, he just told us to go in the lab and do it. With any kind of instructions on how to do it. He told us the right way to do it. It's speculative, just right there sitting down, just crank out numbers and get the right answer. So we first wanted to do it after the pendulum. We thought it was a simple thing, we won't finish the same day, but as you can see, it didn't take that long. I mean, that fast. Moving on. After we gathered the information before, we tried a simple pendulum form, came up with this, we thought it was finished. Got the period analysis that we did. We compared it to our analytical analysis, and with that, we got a comparison of about 15%. Not quite, but we looked at it as, what happened, basically. So we concentrated a little bit, moved on, and thought about a different type of pendulum that might be used in the real world, which is a compound pendulum. As you can see here, in the compound pendulum, there's a design aspect called, it incorporates weight and dimension. As you can see, this mass and length. Moving on, the period that another analysis comes about the same, 4.6. It's an okay analysis, close enough to the right answer. Technically, we did more. We didn't put it into this, got a closer percentage. And I did an inertial analysis myself by hand. Came a little bit closer, but still was good. So after that, we went to the Buay analysis. We just compare the frequency. The goal for this was just to get a torque profile of this. Sorry for walking into the thing. You have to get a torque profile for the output bar, which is this one. And this is the input bar. You have to find out what the torque should be for the output bar using inverse analysis. Basically going from the front to the back and find out what the back is based on what the front is doing. So with the analysis, got the error percentage for the fast one. Got the equation for vector position. Got these equations right here, which is super long. It's like 5 pages long before this one page. After this, we plugged it into Maple, just like MATLAB. Since you didn't have MATLAB on a computer, use Maple instead, and chop out some masses. After that, we have to do a force analysis of each bar, each length, which will take about a good amount of time. Basically, we have to plug it in again, but we don't have enough time, so we're going. So the cylinder and sphere analysis. So the cylinder, same displacement versus time. We got a percentage. Went to the sphere equation. We went to the sphere. We did a displacement versus position versus time graph based on the sphere to see how it moves together with approximation. Compared it with that's the displacement versus time graph. Compared it to the original. And got like 1%. Moving on to the final project. This is the final project that's actually in the lab right now. It's a motion-based platform. A company in Canada. Basically what they're doing in the lab is doing a jaw motion analysis. A jaw moves in 6 degrees of freedom. This is just X, Y, Z, or just X, Y, Z. I'm trying to get to. The basic research that we had to do on this was model and trajectory analysis. These are what it could be used for: light analysis and auto analysis. Basically, just put a car top on, just drop the car and feel like that's in the car, or just drop. Or if you do like what John is doing, the whole earthquake, same exact thing. Basically. This is my design. This is some assemblies that I created. I don't want to show which parts because that would be too much. This is the final product of my design. In SolidWorks, you can actually touch it and it actually moves in each how it's supposed to move. You don't have to do any motion analysis of it and any kind of animation. You just move it and see how it moves. I rendered it. You got a realistic view of the model I created. After that, I tried to do a motion analysis like they gave me, but I didn't have enough time. So I just had these. This is my given, basically, what I already know. Try to computer, but they don't work. China, GA, US students, Nercy, Chris, Buay, and Buay Nhial.
What, are you all tired? No questions?
So, you may have mentioned it, but your final model, how many degrees of freedom? 6. And so you're the only person that has 6 degrees of freedom. How long do you estimate it'll take for you to kind of complete this project?
It's like everything.
Yeah.
Question. How did it seem like before, when you first talked about it, like the sphere gave you guys some trouble because of some single point of contact or something like that? Like what happened differently this time around? Like now it seemed like for the sphere your percentage was like 1 point something percent. So was it like the equations that changed or?
It was SolidWorks. You have to basically, with the program that's not use it right now.
Oh, okay.
That's why.
So you guys got like a better understanding and.
Yeah, the whole virtual thing, you think it'll be easy, just every company just usually gonna bust out like a whole bunch of new products to get rich. It's not that easy, you have to actually know what you're doing. You always get out with everything.
So the 4 of you started out with a similar foundation. What determined the divergent roads that the 4 of you took? Did Dr. Crovey lead you, or did you get to hone in or focus?
Basically the GA PhD student magnet.
Well, basically randomly select the project.
He basically gave us each a different project after we finished the first year, based on how if you liked it or not, who got to pick first.
So does this, your prototype, incorporate like the pendulum,
This prototype thing, or this one?
Yeah.
It's a 4.
that one?
And the
Every so loop plus loop. That was one loop over base. That's just get about so that other loop and everything else is basically the same thing. We think about touching the two the whole motion of the two.
Did you start by working on the parts and finally put it together with the modeling? Yeah, because I started with the parts. You showed just the pendulum, you showed the parts. So finally, at the end, you just put all of them together to get the final, the last one you just showed.
This create each part separate. Okay, and then assemble it together. Then assemble it together to the final position as you see this. And then when we assemble it, to make sure that each part is actually moved how it's supposed to. If you assemble it wrong, it's going to stay there. And just look at it for a good 10 minutes, wondering what you did wrong. Because whenever there's constraints when it comes to something, if you don't put the constraints right, nothing is. So it's a lot of, you just got to know what you're doing, basically.
So is there like a range of constraints? Yeah, like a threshold?
Show them. Do you have on your computer?
There is, right?
Yeah, there's basically constraints. That's like this base cannot move at all. Because the base moves, then everything is going to try to move. So this has to not move. He's only moving this. If you just put a constraint that's only on this, once you move it, it's just move. Like, this cannot tell that it's actually attached to it. When you move it, it's going to just keep going off the screen. And then you move the information, try to fix it. It's going to always trying to do something that's just good to fix.
Is it possible to make a similar platform that has more axes to it?
Yeah.
Chocolate bar part of your project? That's not like a chocolate bar.